Okay, so in this video I would like to calculate the positive predictive value of a specific test. So here we have this nice matrix, and in this matrix we have two variables represented. So it's a cross tabulation with two binary variables. The first binary variable is the test result. We have test positive, so out of 7,500 individuals, 2,600 test positive and 4,900 test negative. And we also see we have disease status, which is also binary. We have 2,500 individuals are positive for the disease and 5,000 are not positive for the disease. So what we're going to do is calculate sensitivity, specificity, and the prevalence of the disease. So this is an estimate of the prevalence of the disease, given this is a sample, so that we can go ahead and calculate the positive predictive value using Bayes' theorem. Okay, so let's go ahead and do that. So the sensitivity of the disease, this is a measure of how well a test detects individuals who actually have the disease or true positives. So in this case, sensitivity would be our denominator for this measure. This is a proportion. Our denominator would be the total number of individuals who have the disease. That's 2,500. And the amount who test positive are 1,800 among those who have the disease. So all we have to do then is to get the sensitivity of this test, we have to divide. Let me find my mouse here. So sensitivity. Sensitivity is equal to 1,800, we said, divided by 2,500. And we take out a calculator and do that. So it's 1,800 divided by 2,500 divided by 2,500. We get 72%. So our sensitivity is 72%. 0.72. Our specificity, not the neatest writer in the world, but right? Specificity is true negatives. We want to see how many individuals who do not have the disease are correctly classified as not having the disease. If we go back to our cross tabulation, we have 5,000 individuals who do not have the disease, and 4,200 are correctly identified using our test. Of course, in reality, we wouldn't know if they're correctly identified or not unless we were conducting some kind of a validity study. Sensitivity and specificity are characteristics of the test, right? They're characteristics of a test in terms of validity. So we have to divide here 4,200 divided by 5,000. So we go back to our, whoops. Oh boy, that's my little rocket launcher when I get mad at people. So 4,200 divided, someone be, yes, I am. So 4,200 divided by 5,000, 4,200 divided by 5,000, and that equals, so let's go back here, 4,200 divided by 5,000, get 84%. Okay, so we have two important measures here that we can use later. So these are modest indicators of sensitivity and specificity. So when we say our sensitivity is 72%, we'll make a correct true positive at 72% of the time, but we'll also unfortunately make mistakes and have false negatives saying that individuals don't have the test when the disease when indeed they do have the disease. And you can imagine the ramifications of that. Like if somebody's HIV positive, we say, oh, you don't have HIV, one may go out and engage in unprotected sex and spread the disease. So same with specificity, we have 84% specificity, so we will correctly identify individuals as not having the disease in 84% of the cases, but in 16% of the cases we'll have false positives. In that case, we're going to tell somebody that they have the disease when they actually do not have the disease, and that's not a good state of affairs either. They might actually stress somebody out, or who knows what. Okay, so we also need to know what the disease prevalence is. We're going to get an estimate of the disease prevalence, so that's the amount of proportion of individuals who have the disease. In this case, that's simply 2,500 divided by 7,500. So that's an easy one here. 2,500 divided by 7,500, and you get 33%. Okay, so we have three measures that we need in order to calculate positive predictive value. So here we have prevalence, right? Prevalence is equal to, you said 0.33. All right, 33%. So now we can calculate our positive predictive value. We can do it in two different ways. We can actually calculate it directly from our table here. In this case, it's the amount of individuals who have the disease who test positive, out of those who test positive. So we're trying to see how well the test predicts disease status. So we have 2,600 individuals who test positive for the disease, and out of those, 1,800 are correctly classified as being diseased. So it's 1,800 divided by 2,600, right? So we have 1,800 divided by 2,600. So we get 69.69. So we could just start by saying that our positive predictive value is 0.69, right? I'm trying to avoid hitting that button again and launching a missile. Okay, so we get, was it 1,800 did I say? I forget so easily. 1,800 divided by 2,600. So we have 1,800 divided by 2,600 equals, is it 0.67 or something like that? 0.69. All right, so let's see if we can replicate this using this formula, this other formula. And the advantage of this formula is that at times you're not going to have all the information available, including the sample size or population size, but what you will have is you'll have indicators of, all you need is indicators of sensitivity, specificity, and prevalence, and we are good to go. So let's go ahead and use Bayes' theorem, and indeed for my class I did ask individuals, or this will show here, to predict the positive predictive value using the formula. Okay, so let's go ahead and do that, and here I am searching again. So I'm going to clear this because I have all this information stored somewhere. Alright, so we have a conditional probability. We call this Bayes' theorem here. So Bayes' theorem. We have the probability of, and we're going to try to stay consistent here. I want to use the same language I'm using everywhere else. A given B is equal to the probability of the intersection of these two events, A intersection B, divided by the probability of B. If we're going to put these in terms of our work here, so the probability of A given B for the positive predictive value would be the probability of correctly identifying someone who has the disease given one tests positive using whatever test we're dealing with, right? So it's the probability that an individual has the disease given he or she tests positive. So that's the probability of the intersection between the two, which is has the disease and testing positive, divided by the probability of testing positive for the disease. So this numerator, you can expand it to equal the, again, I want to stay consistent here, probability of B given A times the probability of A divided by the probability of B. So this then would be the probability that one tests positive given one has the disease, multiplied by the probability that one actually has the disease. So let's just say A has disease, B is equal to test positive. Okay? Alright, so now I expanded this probability here, intersection B, right, into probability of B given A times the probability of A, right? So this comes from the multiplication rule, where the probability of B given A is equal to, see if we multiply both sides, excuse me, if we divide both sides by the probability of A, right? These would cancel out. What we'd get is this probability of B given A, so contingent on A is equal to probability of A intersection B divided by the probability of A, and that's what we have up top there, right? All right, so right now we've done much of the work we need here, at least for the numerator, so let's go ahead and expand this denominator. So this denominator here now is the total probability of B, the total probability of B. So here we have a Venn diagram, right? So we have B and we have A. So we know as A is that individual has the disease and B is that the individual tests positive. So these can overlap, like one can have the disease and test positive, right? So they can overlap. What we're interested here is the total probability of B. So this little chunk here of overlap is probability of B intersection with A, right? It's the intersection of the two, right? So we know that this probability of B is going to include several, well, at least two different facets, because it's going to include the part it shares with A, right? So this is the probability B intersection of A, and it's also going to include the part that it does not share with A, right? And these two are mutually exclusive, so B intersection of A cannot co-occur with B, the intersection of the part that's not A, right? Let's say that's P, probability of B intersection not A. We use a symbol for not A. All right, so the total probability of B, this probability of B, is going to equal this part of B that is shared with A, so it's the probability of B intersection with A plus this part of B right here that is not shared with A. So it's the probability of the intersection between B and not A. These two cannot occur together, they're mutually exclusive, so we can use the addition rule. To calculate the probability of either of these two occurring. Okay? The probability of B intersection A or the probability of B intersection not A. And those two are exhaustive events within this sample space, right, of B. So you either have B intersection A or B intersection not A. Those are the only two elements that we have here. So that sums up to the total probability of B. Okay? So now we have our formula set up. So I'm going to move to I'm going to have to erase due to lack of space here. So let me go ahead and erase this. So I'm going to edit clear. Alright. So let's go back and finalize our formula here. So we have the probability of B given A is equal to the probability of the intersection of B and A divided by the probability of B, which now we can state as probability of B intersection with A plus the probability of B intersection with not A. Okay, there you go. Looking pretty good right now. So now we can go ahead and expand this completely here, so that we'll say the probability of B given A. Actually, you know, let me yeah, we'll keep it this way just to stay consistent. Yeah. Actually, no. Let me erase this part right here because I want to stay consistent. So, is this my eraser? I think so. Yes, because see here, it's actually the probability of. I'll Let's erase this. Can't change what I'm doing in midstream. So this is the probability of A, right? One has the disease given one tests positive, because this is the probability of B in the denominator. That's why. So A given B. Okay. So here we go. So now we have the probability of this intersection between the two. Let's expand that to be probability of B given A times the probability of A, right, divided by probability of, so this is the same, right? These two are the same. So probability of B given A times the probability of A. We're going to add that to its complement, right? As again, we know that they're mutually exclusive, so the probability of B given not A times the probability of not A. All right. That's our formula. Okay, now we're going to go ahead and change this formula to terms of our task here, which is to calculate positive predictive value. So I'm going to change my terminology here, or my terminology, my symbols, whatever you want to call them. Okay, well, we'll start with this. So I'll continue using this until I run out of space. So positive predictive value is equal to probability that one has the disease, we'll call it disease positive, given that one tests positive, right? Okay, that's what we're trying to calculate. And that, my friends, is equal to probability of one being, or the intersection between being disease positive and testing positive, right? Divided by the probability of testing positive, right? Testing positive. Alright. So now we're going to go ahead and clear this again so that we can move, so I can have a full page to work with. So I'm going to clear this and let's keep on going here. So we can expand that formula for P to equal to the probability that one tests positive given that one has the disease. You should know what that is, given what I said earlier. It's the sensitivity of a test, right? Times the probability that one has the disease, one is disease positive, which is the prevalence of the disease, right? And we notice that we repeat that here, so it's probability of testing positive given one has the disease multiplied by probability that one has the disease. So let's just erase this here real quick. You see I forgot the P here. Yes, I forgot it. Okay, so let's go back to our pen. Ain't technology wonderful? Probability that one has the disease. Okay. Times the probability that one has the disease. And we add to that, we'll make this a little longer, we add to that the probability of testing positive given one does not have the disease. So one is disease negative, right? Has a probability that one is disease negative. Okay, so now let's substitute the terminology. Man, I'm a messy writer. I'm trying my best, though. Let's substitute the correct terminology for this from epidemiology. So we have this numerator, which testing positive given one has the disease is one sensitivity. So we have sensitivity. We're going to multiply that by the probability of having the disease, that's prevalence. Right? And we're going to divide that by the sum of sensitivity times prevalence. Right? sensitivity times prevalence. And now we have to deal with the opposites. What's the probability of having a disease given that probability of testing positive given that one does not have the disease? That's actually a false positive result. That's a false positive result. So if we go back to our table here, so you can see somebody who tests positive for the disease but does not have the disease is a false positive. So these individuals in this column do not have the disease, but with the nexus of that column and this row is 800. So these 800 individuals are false positives. So we can call them false positives, but these are also, if we know our rules of probability, you have two possible options among individuals who have the disease. Either you can have the disease, either you can test positive when you don't have the disease, or you can test negative, which is a true negative, and not have the disease. So false positive and true negative are mutually exclusive, and those are the only two possible events here. So this is an exhaustive set, right? Sample space. So therefore, we know that. So given that we know that our sensitivity, our specificity was 0.84. So 1 minus 0.84 is 0.16. So the probability of a false positive result is 16%. So we're going to just go ahead and call that false positives, right? So we have false positives, right? And then we're multiplying that times 1 minus the prevalence of the disease. Go, because this is the probability of being disease-free. It always reminds me of a scene from Old School. If you've ever seen the movie Old School, when there's a Mitch Martin party, one of the characters says, and there's Mitch Martin, he's that disease-free gentleman standing over there. So this is for Mitch Martin. Okay, so let's go ahead and put in all the numbers here. So PPV equals sensitivity times prevalence. We know our sensitivity is 0.72, and our prevalence is 0.33, and we knew down here that we have the same 0.72 times 0.33, and to that we're going to add false positive rate, which we said was 16%, right? Because our specificity was 84%, so this is 0.16. We're going to multiply that times 1 minus the prevalence. So if our prevalence is 33%, so 66% would be 1 minus the prevalence, so 0.66. And that should give us our result. So let's go ahead and do that. So our numerator is 0.72 times 0.33, which equals 0.24. 0.24. We're going to divide this by 0.24. Again, this is a repeat. And we're going to add to that 16% times 66%. 66 times 0.16 equals 0.1056. So let's go ahead and do that. 0.1056.11. Okay, 0.11. So this then is 0.24 divided by, and in parentheses we have 0.24 plus 0.11. Close those parentheses, equals 60, basically 69%, right? 69%, 0.69. All right. 69%, I said. And what did we get originally? Let's see if we match that. So we had 1800 divided by 2600 equals 69%. Booyakasha, respect. We got it, okay? So there you go. That's how you calculate positive predictive value, my friends. And you can see that it's just a matter of having the numbers. You don't have to go through that whole making that table, although you can. That's your choice. But if you don't have the you can make up your own sample or whatever you want, but if you have these data available, like prevalence, the specificity and sensitivity, you can just use this Bayes' formula to calculate it. All right, thank you. Bye. I hope you enjoyed it very much. I did.